Окей. Перш за все, я хотів би висловити свою вдячність організаторам за можливість виступити з доповіддю на цій дуже презентабельній конференції. Я сподіваюся, і не впевнений, що усі наступні алгебраїчні конференції в Україні пройдуть під чистим і мирним небом в Україні. Слава Україні! This talk was developed and prepared together with Leonid Kurdachenko. I will start with the definition. A left break is a set A with two binary operations, addition and multiplication, satisfying the following conditions. A is an abelian group by the addition. A is a group by the multiplication at the same time. And this is some kind of distributive properties that are talking about A times B plus C, AB plus AC minus A for every A, B, C from A. Wolfgang Ramm introduced braces as a generalization of Jacobson radical ring to study the theoretical solution of the Young-Baxter equation. This is the work in which this idea, this notion was introduced. First work in 2005, one work in 2007. I believe in 2006 we have another work in the algebra and discrete mathematics. Subsequent papers describe connection between braces with other algebraic structure was done by Wolfgang Ramm in 2007, few of them, 2008, and so on, 2009, and so on. Just a second, I will make it. Oh, just better. One of the immediately arising question is about the study of the braces generated by one element, which is a very, very natural question. In every algebraic structure, it's interesting to find out what happened if the structure is generated by one element, and maybe this is the first questions that come to mind. In general, this task turned out to be quite difficult, very difficult. So the study of one generated braces should be done under some additional conditions. Let A be a left brace. A subset S of this brace A is called subbrace, more precisely left subbrace, if S is a left brace by operations given on A, which means S is a subgroup of the additive group of A, and at the same time is a subgroup of the multiplicative group of A. The next idea was, I believe, the key idea in the next step of study braces and very useful. It's lead us to the special operations that we will introduce right now. Let A be a left brace for every element A. We define the function. We define the function A to itself by the rule. We consider the function lambda AX such that AX minus A for all elements X from A. Let A be a left brace, put A star B, a new operation connected using this two operation is given, which is a product AB minus A minus B. We can see that A star B is lambda AB minus B. Thus, for this distributive property, now we have a very natural expression. A star B plus C equal A star B plus A star C. A left brace A is called trivial or abelian in this case if A star B equal to 0, or, which is the same, A plus B equal to AB. For all elements AB from A, the subbrace L of a brace A is called an ideal of A if A star Z and Z star A belongs to L for all elements L. If K and L are subbrace of A, we denote K star L the subgroup of the additive group of A generated by elements X star Y, where X from K and Y from L. So if A be a left brace, we put A in the, I just would like to focus your attention, A in the parenthesis power of 1, I mean, A to the power of 1 in parenthesis equal to A, and recursively, A to the power in the parenthesis alpha plus 1 alpha is A in alpha parenthesis star A for all ordinals alpha, and of course, for the limit ordinals lambda, we use an intersection of all these substructure subbraces in the less than which indices less than alpha, less than lambda. We know that A in the power alpha in the parenthesis is an ideal of A for every ordinal alpha. A subbrace L of left brace A is called a left ideal. It's a different left ideal if A star B belongs to L for all element alpha and for every element B. In this case, we introduced A sub 1 without parentheses equal to A, and recursively A alpha plus 1 equal to A star A alpha. And again, for the limit ordinals, we are considering intersection. Let A be a left brace and S be a family of subbraces of A. Then the intersection of S of all subbraces of this family S is a subbrace. If we consider a subset M of subbrace A and consider the family MB, all subbraces of A containing M, then such intersection of this family is the smallest subbrace of A containing M. This subbrace is called the subbrace of A generated by the subset M and will be denoted by this symbol. A subbrace S of a brace A is called finitely generated if there exists a finite subset M such that A generated by this finite subset. If this subset consists of one element A, we are talking about a one generator brace. And even though this restriction is not enough to get a really meaningful results from this definition. So by now, it's natural to consider this specific one generator brace, imposing some additional restriction. In this current article, the main ideas will be dedicated, the main result will be dedicated to such brace in which we have the following restrictions. A to the power 3, which means you multiply A 3 times by itself as a star operation, is 0. So one can find the proofs of the following result in the paper of Svidot and Jasper van Antwerpen and van der Meen. This last one is published yet in the archive, but it's a very interesting article, and I'm sure will be published as soon as some peer review sources. And the proposition that was, you can find there, it's just preliminary results that shows us how to operate with the star operation efficiently. First of all, again, the distributed property looks very natural. Next, if you consider the property of multiplication, the product by the star operation C, you can use the following formula. The same if you would like to multiply the sum, and two more formulas for the sum additional function property of on the star operation products. Okay. The proof of the following useful result is possible to find in the paper of Sidon, which is published in 2018 in the Advances in Group Theory and Application. Its proposition, let A be a left brace, L be a left ideal of A, then the product L star A and A star L are left ideals, both of them, of A. Moreover, L is an ideal of A, then if L is an ideal of A, then L star A is an ideal of A also. Using these two propositions that we mentioned right now, we obtain the following. Let A be a left brace, then A to the power of alpha is a left ideal of each ordinal alpha, and A to the power of alpha in the parentheses is an ideal for each ordinal alpha. A brace A is called soluble if A has a finite series. 0, A sub 0, A sub 1, A n minus 1, A equal to A itself, of ideals whose factors are abelian for all J between 1 and n. Next results could be considered like preliminary results that help us to get some more specific and detailed information regarding the structure of the braces that we decided to describe today. Proposition, let A be a left brace, and suppose that A cube, A to the power 3, A cube can be said, equal to 0. Then A square is abelian, Moreover, X times Y star Y equal to 0, or which is XY equal to X plus Y for every element X of A and Y of A square. XZ star Y equal X star Y Z plus Z star Y for all elements X, Y, Z. And G to the power N star Z could be represented as N times G star Z for every integer N. Next, let's A be a left brace and suppose that A cube equal to 0. Then A to the power M has a presentation like MA plus 1/2 M square minus M, A star A for every element A of A and every integer M. Next proposition, it's about multiplication of the elements with the coefficients n and k. This is the formula. I will skip the reading because it's not fun to read this formula. For every element A of A and any integers n and k. Next proposition, let A be an element of such brace and put A1 equal to A, A2 equal A star A, A1 equal A, A2 equal A1 star A, which means that you multiply by A with the help of star operation from the right. Then the subbrace of A generated by the element A is a subset consisting of elements having the following form. This is the sum of KJAJ, the sum, linear combination, whatever. Kj belong to Z is integer, and Kj not equal to Z only for finitely many J of n. So it's a linear combination, but not zero elements for finitely many, only finitely many J indices. Like in other algebraic structure, there is the concept of nilpotency in braces. In the theory of braces, there are different approaches to this concept. First of all, we can mention the article CEDAW, 2018 CEDAW, Gatila Ivanova and Agata Smoktunovich in 2017. CEDAW, Smoktunovich, when the mean scalar braces of nilpotent types proceeding from the Mathematical Society in 2019, very fresh result. Jasper van Antwerpen is again the same article that I mentioned it, I will mention it later from the archive. And we will use the following notion of nilpotency, introducing the paper Smoktunovich, dated 2018. We will say that a brace A is a Smoktunovich nilpotent if there are positive integers and k, such that A to the parenthesis n power parenthesis n equal to 0 and equal to A to the power k with no parenthesis. We denote by the n indices n of nk the class of the left braces satisfying the conditions that we mentioned, where n and k are the least integers, preserving this property. We have the following result. You see, it looks, I would not say that it looks very elegant, but this is important information which can help us to understand how the elements of the left brace A with a property A cube equal to 0 looks like. Suppose that A is related by element A, which we are talking about one generator braces, and put A1 equal to A2, we multiply every time from the right, which means we multiply from the left result, multiply new A. Then every element of A has a form. K1, A1, K2, A2, K3, A3, where K1, K2, K3 are integers. Moreover, if X equal to K1, A1, K2, A2, K3, A3, and Y equal T1, A1, T2, A2, T3, A3 are elements of A, whereas all of them, K and T's, are integers, we have X star Y equal to product T1, K1, A2 plus F 2K2 plus K1 minus K1 squared T1, A3. And XY regular without star looks like that. Let me just show this without reading. I mean, the formula without reading is clearly understandable without reading. In particular, if A3 equal to 0, then every element of A has formula K1, A1, K2, A2. Of course, K1, K2 are integers. Moreover, if X equal K1, A1, K2, A2, Y equal T1, A1, T2, A2 are elements, and these numbers are integers, then X star Y equal T1, K1, A2, X, Y equal K1 plus T1, K1 plus K2 plus T2 plus T1, K1, A2. This is, I would say, the main result in these investigations. Next is a very interesting. Furthermore, A is a Smaktunovich nilpotent. More precisely, A belongs to the class NS33 whenever A3 equal to 0 and A equal NS43 whenever A3 is not equal to 0. Next two results, it's about existence of some specifically mentioned braces type. There exists a one generator left brace G equal Cartesian product Z times Z, where the addition and multiplication are defined by the rules. K1, K2 plus T1, it's like coordinates, addition of coordinates. To be considered, and this one, another formula, not just coordinate multiplication, it's more complicated. The first coordinate we are adding, the second coordinate we are multiplying and adding the second coordinate. If A is an arbitrary one generated left brace, such that A belongs to the class 33, then there exists an epimorphism of D to A. Theorem B, it's related to the same kind of equations, but for the three-dimensional case. This is the formulas for this case, and let me skip the reading of this. We can see that the left brace constructed in theorem B1 and respectively in B2 is a free one-generated left brace such that A cube equal to 0 and equal to A cube in parentheses, and respectively for the second case to A4 in the parentheses. Would you be so kind to tell me how much time do I have left?
You have 4 minutes.
4 minutes, good. I will try to do my best. So it's next section I would like to consider is a star central series and braces. First of all, we consider the notion of the star center. Sounds like in Hollywood. Okay, theta star A is a set of all elements A of the left brace end, and A star X and X star A equal to 0 for every element X of A. And AX and A plus X equal to XA for every element X of A. This is called the star center. This definition implies that the center of multiplicative group A includes the star center of A, and note that zeta of the star center is an ideal of A. We will denote by zeta A just the center of multiplicative group of A. So based on it, we constructed the upper star central series. It's very understandable how it was done. It was done in this way, and we considered the recursively that zeta alpha plus 1 over zeta alpha is zeta of this factor brace. For all ordinals alpha, and for the limit, we consider it union of the limit for the all ordinals before this. By definition, each term of the series is ideal. The last term of this series is called the upper star hypercenter. By the remark above, the upper star series is a changing central series in the multiplicative group. So based on this definition, we are trying to build up the upper central series of brace L, and okay, I am just inside note, I believe. So let me jump to show you the theorem C, which is also could be found in different formulation in this article from the article. As I saw to you, it's the lab brace has finite central series if and only if it's not numerically important. And if a lab brace is not numerically important, then the multiplicated group of A is important. And if a lab brace is not numerically important, then the periodic part of the additive group of A is an ideal of A. I just would like at the end to mention, I'm over, my time is over, and I would like only to say that we consider also star hypercentral series, and we obtain the following characterization of the hypercentral series. I don't have time anymore to read them out. Thank you very much for the listening. I appreciate it. That's it.
Thank you very much.